Okay, the purpose of this little presentation is to quickly review linear elastic stress analysis. And starting with one-dimensional stress and strain analysis, I'm sure I don't really need to remind you that in one dimension, stress can be simply defined as force over cross-sectional area, and strain can be defined simply as change in length over original length. And the relationship between stress and strain is given by Hooke's law, which states that the stress is equal to Young's modulus times strain. And that applies if we are working in the linear elastic region. Moving on to two-dimensional stress and strain analysis. An example here is a thin-walled cylinder subjected to internal pressure, and the stresses in the wall of that cylinder can be described as circumferential and longitudinal stresses, which are perpendicular to each other at any point in the cylinder wall. Those stresses obviously have got different directions, and they will also have different magnitudes. Now, to be strictly true, we really ought to define the shear stress that goes with those two directions as well. In this case, that shear stress is 0 because we're not applying any twisting to the cylinder. If we didn't define the stresses in those two directions, then remember that the shear stress wouldn't be 0. Another example here, we got this is the result of a fine and Thumb analysis of a simple plate with a hole, just a quarter of the plates shown here, and on the left hand side here, this plot showing the stress in the horizontal direction, the x direction, and on the right hand side we're showing the stress in the vertical direction, the y direction, and we can see that the magnitude of the stress is quite different between those two directions. So once again, highlighting the fact that stress magnitude is dependent on the direction in which we're looking at the stress. In three dimensions, things get a little bit more complex again. Here we've got three direct stress components, usually referred to as the x, y and z stresses, and associated with them we will have in total 6 shear stress components, although they can be paired up. Equilibrium of that little element on the right hand side there dictates that the shear stresses must pair up. So we actually need to only define 3 shear stress components. But all 6 stress components, the 3 direct stresses and the 3 shear stresses, are needed to properly define the state of stress at a point within the material. The relationship between stress and strain in 3 dimensions is obviously going to be more complex because we've got more components to deal with, but it's a version of Hooke's law, and the material properties we need to relate the stresses and the strains are the Young's modulus and the Poisson's ratio, and the 2-dimensional version of Hooke's law can be extracted from these equations just by removing, say, the z component and the shear stresses in the z direction. Okay, that was a quick reminder about some of the basic principles of linear elastic stress analysis.